All right, so we're going to take a look at some more derivative rules today. We're going to look at derivatives of constants, derivatives of a sum or a difference, and a constant multiple. So we're going to see each of these here. So the derivative of a constant, okay, a constant function is some sort of a horizontal line. And we saw in a previous lesson that the derivative of a horizontal line is just 0 because a horizontal line is flat, and so we can say that the derivative of any constant is equal to 0. It doesn't matter what that number is. Okay, so if my function was y equals 3, then y prime is equal to 0. If my function is y equals pi, pi is just a number. That's a flat horizontal line, so the derivative is still 0. All right, that's the first one there. The constant multiple. Okay, a constant multiple basically means, you'll notice I've got a u in here, not an x either. So that u value represents any function I can come up with, and that function is being multiplied by some value of c. So what this looks like is, and I'm just going to give the example here, and then we'll talk about it. So if I had a function like just something super simple, y equals 3 times x to the 5th. If you remember from the previous lesson, we would find the derivative, y equals, and that 5 drops down and multiplies by the 3. So I can bring the 5 in front of the 3, I can put the 5 after the 3, but really what I can do is I can say, look, in fact, I'm going to erase something. I'm going to take the derivative of x to the 5th, which is 5x to the 4th, and then I'm simply going to multiply that by the 3 that was there to begin with. It's exactly what we were doing yesterday. Oops, that's y prime. So we know that y prime is going to equal 15x to the 4th. That's what a constant multiple is. It means, look, you can keep the c there, whatever that c value is, and you can multiply it by the derivative of whatever function you're dealing with. Okay, seems like an odd rule maybe, but you'll get used to it. Next one, the derivative of a sum or a difference. Okay, so u and v represent two different functions, completely different functions, but if I'm taking the derivative of a sum or a difference, I can take the derivative of the first part, du dx, and I can add or subtract the derivative of the second part, dv dx. And we're going to see that in our very first example here. All right, so we have y equals 2x squared minus 5 over x plus 6. First thing I want to do is get that x back up to the top, so I'm going to rewrite y equals 2x squared minus 5 times x to the negative first power plus 6. Now we can take the derivative. Y prime equals, bring the 2 from the exponent down in front, multiply it by the 2 in front. That's 4x. Subtract 1 from the exponent. I just put the 1 there so you can see it. You don't need it there. Do the same thing on the next one. Bring the negative 1 down, multiply it by the negative 5. You get plus 5 times x. Subtract 1 from the exponent. That goes to negative 2. And then the derivative of 6, which is a constant, is 0. Now, you can leave it like that, or you can simplify it. Y prime equals 4x plus 5 divided by x squared. Both of those would work. I would encourage you to turn off the video, try the next one on your own, see what you can do. All right, I'm going to start by rewriting y equals 8 times x to the 1/2 power. Remember, we don't want those square roots. Minus, and this middle one seems to trip a lot of people up. So I'm going to rewrite the middle one as 1/3 times x to the 6th power. Those two notations mean the same thing. Plus 2 pi to the 5th power. Let's take the derivative. Y prime equals, I'm going to multiply 1/2 times 8. Half of 8 is 4. Times x. I'm going to subtract 1 from the exponent. That's negative 1/2. I'm going to bring the 6 down and multiply it by negative 1/3, so that's negative 2x. Subtract 1 from the exponent, that's 5. And guess what the last piece is? You're not going to bring the 5 down in front because pi is just a number. This whole mess in the back here, this is just a constant, and that constant is 0. If I needed to clean this up, if, I say if because a lot of times we don't, sometimes we do, I would bring the x back down in the denominator, x to the positive 1/2, but the second term is going to stay exactly the way it was. There's no negative exponent there. All right. Oh, and by the way, this other term on the bottom here, x to the 1/2, I could also write that as y equals 4 over the square root of x minus 2x to the 5th power. Okay? Just got to know that. That's an or in there. You can do either one of those. All right, our next section talks about horizontal tangent lines. So when does a function have a horizontal tangent line? Well, it has a horizontal tangent line. The slope of a horizontal tangent line is 0. To find where a function has a horizontal tangent line, so let's go over to our graph and draw one of these. So right at the top of this curve right here, if I drew a tangent line, that would be horizontal. This point is at a maximum. If I go to the other side here, I would have another horizontal tangent line. That point there is a minimum. So if you have a max or a min on a graph that's differentiable, there will always be a horizontal tangent line. We know that the slope of this is equal to 0. So if I want to find where a function has a horizontal tangent line, I am going to set the derivative equal to 0. And that's what we're going to do in number 3. Number 3 says, find the x values of any horizontal tangent lines of f of x equals 4x squared plus 7x minus 13. Well, the first thing we need to do is we need to find the derivative. So we're going to find f prime of x. We're going to use our rules. So this first one, we're going to multiply 2 times 4. That's going to be 8x. That's going to be to the 1st power now. The derivative of 7x is just 7. And the derivative of negative 13 is 0. So I don't need that on the end. I want to find out when this derivative is equal to 0. So I'm going to set it equal to 0, 8x plus 7. To solve this, I'm going to subtract 7 and divide by 8. Negative 7 divided by 8 equals x. So if I were to graph that particular parabola, I would find out that at the bottom of that parabola, okay, so draw a little picture here, and I don't know how far down that thing goes. It goes down pretty far. I know that just because of the negative 13 here. But at x equals negative 7/8, so if this was negative 1 right here, somewhere down here at negative 7/8 is the bottom of that parabola. Okay, and it would do something like that. All right, let's keep going here. Okay, is the function f of x, and they give you a piecewise function, differentiable at x equals negative 1? Okay, so is it differentiable at x equals negative 1? Okay, well, first of all, we need to know, is f continuous? At x equals negative 1, because that's where the function splits. So we need to know, is it continuous at x equals negative 1? Okay, so continuity. All right, I'm going to start on the left. So continuity, continuous. Because if it's not continuous, we can stop right there. So to check for continuity at x equals negative 1, what I want to do is I want to look at the limits. I want to look at the limit as x approaches -1 from the negative side. So I'm going to be using the top function, 5x squared plus 3x plus 2. And so if I plug into that function, we would get 5 times -1 squared plus 3 times -1 plus 2. And if you finish off the math there, you actually get 4. I do the second function, same thing. So I'm looking for continuity here, right? If it's continuous, then the limit has to exist. Okay, so that's one of our continuity check marks here. So we need to approach -1 from the positive side. That's the second function, -7x minus 3. And I think it's pretty easy to see in this case that if I plug in -1 and I multiply by -7, that's 4, and 4 minus, or excuse me, is +7, and 7 minus 3 is 4. So the limit exists. Okay? Now, the limit exists. Am I defined at f of -1? So f of -1. And hopefully you're already sitting there going, well, yeah, Mr. Cornelius, I'm defined at f of -1 because I've already plugged in -1 to the second function here. We just did that when we found the limit of the second part. So this is also equal to 4. So I can say f is continuous. And because the limit is equal to where I'm defined. Okay, so that's number 1. I need to show that I'm continuous. If I'm not continuous, I get to quit right there. Okay, the other thing that I have to check for here is, are the derivatives equal? Are the derivatives equal? In other words, you remember our sharp turns. If I have an absolute value function like that, the derivative over on the left is negative, the derivative on the right is positive, and so I don't have that particular, this would not be differentiable in that case. Okay, so I need to find the derivatives. So we're going to do that next. I'm going to do f prime of x, and f prime of x is also going to be a piecewise function. So we're going to take the derivative of the top function. That's 10x plus 3. We have the same restrictions, x less than -1. Our second function, the derivative of -7x minus 3, that's just -7. All right, there we go. And the restriction on this one is that x is greater than or equal to -1. All right, so I need to know if those are equal. I need to know if the limit, again, we're talking about limits, as x approaches -1 from the negative side of f prime of x. So that's my first function. And actually, instead of f prime, I think I'm actually just going to put 10x plus 3. I need to know the limit of that part. So I would plug in -1. That would be -10 plus 3. So that's -7. And then I need to find out if the limit of the other function is the same. The limit as x goes to -1 from the positive side, which is the function -7. So that's always equal to -7. That's the derivative. Remember, I'm not taking the derivative of -7. That is the derivative. These two derivatives are equal, so f is differentiable. So I need to show that it's continuous. If it's not continuous, I quit. And then I need to show that the derivatives are equal to each other as well. Okay, so a slightly different question down below, very similar but slightly different. It says, what values of a and b would make the function f of x differentiable? So in order for f of x to be differentiable, it has to be continuous, and the derivative has to be equal on both sides of the function as well. So in the last one, I actually showed continuity by showing the limits on each side. This time they're saying, look, you got to find these numbers, number one, that make it continuous. If a function is continuous, a piecewise function, that means the left side of the function has to equal the right side of the function. So the first thing I'm going to do here is I'm going to try and find continuous. I'm going to set the left side, x squared minus ax plus 2, equal to the right side, x plus b. I'm going to set x equal to 3 because that's where this function splits, is x less than 3, x greater than 3. So I'll do 3 squared minus a times 3 plus 2 equals 3 plus b. Now I can already see that I'm going to have a problem here because I've got an a and a b in here, but I'm going to go ahead and clean this up anyway. This is 9 minus 3a plus 2 equals 3 plus b. Let's see, 9 plus 2 is going to be 11 minus 3a equals 3 plus b. Subtract the 3 and I get 8 minus 3a equals b. So again, I'm kind of stuck right there. So I can hold off on that for a minute, and I'm going to jump to the other side and talk about differentiability. Differentiable. So let's first, in order to figure out if we're going to be differentiable, we need to find the derivative. So f prime of x. Again, this is a piecewise function, so the derivative of x squared is 2x. The derivative of a times x is just a, because remember a is a constant, okay? And the derivative of 2 is 0, so that one's done. This is for x less than 3. The second function is x plus b. The derivative of x is 1, and the derivative of b is 0, so the b is now gone. We have x greater than or equal to 3. And I can set those equal to each other because if I'm differentiable, the two parts of the derivative have to be equal to each other as well. So I can do 2x minus a equals 1. This one I can definitely solve. I'm actually going to, let's see, we need to be differentiable at x equals 3. So I might as well do that first. 2 times 3 minus a equals 1. This is 6 minus a equal to 1. I'm going to bring a to the right, and I'm going to subtract 1 to the left. So a is equal to 5. So I know I'm differentiable if a is equal to 5, and since a is equal to 5, I can now come back over here, and I can say, okay, if a is equal to 5, let's plug in 8 minus 3 times 5. And that's the value of b that's going to make me continuous. So we get -7 equal to b. That was a fun one, wasn't it? See you next time.